In this chapter, we're going to talk about processes. Actually, we've discussed processes slightly in the previous chapters, but now we're going to look at them in more detail. So we'll first talk about the concept of a process and how we do scheduling. Note that we're going to discuss scheduling actually in much more detail in chapter 6, but also in this chapter we'll slightly talk about process scheduling and operations on processes, which will be followed by the inter-process communications, IPC. We'll give some examples, and finally talk about communications in a client-server architecture, where we have typically multiple clients trying to communicate with a single server process. The objectives in this chapter are, first of all, we're going to define what a process is. Simply, a process is a program in action. You have a program on the disk. When you run the program, then you get a process out of it. We will describe the various features of processes. So, how you create a process from a program. When you have multiple processes in memory running, which one goes to the CPU, so the scheduling of the processes. While these processes are running, they can communicate with other processes. And also, when the event is the end of the program, or if there is a catastrophic failure in a process, then how do you terminate the process? We will talk about inter-process communication using, for example, shared memory and message passing. And we will also, as we said, discuss client-server architecture. So, if you look at the operating systems literature, you will see that typically we use terms like jobs, user programs, tasks, or processes. The way these terms are used really changes from textbook to textbook, but in general, we talk about jobs when we're talking about batch systems. Remember what a batch system is. If you have an interactive system, which is the time-shared system in the second bullet, we're talking about a system like a desktop computer or your laptop, where there is a human being directly using the computer system. So the human being takes an action and immediately expects the result of that action. Like you click a button and you expect, for example, a window to pop up or some calculation to be done. So such systems are interactive systems. In the case of interactive systems, the more important thing is the system should be responsive. That means when you do something, when you click the button, you immediately wait for the response. So it has to be responsive. Whereas in the case of a batch system, the first bullet, now we don't care so much about interactivity because actually there is no human being sitting in front of the computer just counting the seconds for the task to be completed. In that case, for example, you have many people who want to, many users who want to get their programs run. Typically, these programs do not require interactivity. So you just say, run these simulations for me, or calculate the balances of all accounts in a bank. Or, for example, if you're trying to grade the exams of, say, 500 students, you just give all the student solutions and say, evaluate all of these student submissions. Now, these are non-interactive systems. These are called the batch systems. In the case of batch systems, we call it a job. In the case of a time-shared system, we call it a user program or a task. But in general, we typically use job or process terms in an interchangeable manner. So we will stick with mostly the term process here, but you will once in a while hear me using the word task. It's just the same thing for us for the moment. So a process, as we said, is a program in execution or a program in action. So the process execution should progress. That means instructions should get executed one after another and typically in a sequential fashion. But of course, some of these instructions will cause jumps, like in the case of a conditional statement like the if then else statement, or in the case of a loop where you jump to the beginning of the loop or you jump out of the loop. But typically it's sequential. When you look at a process, we talk about the memory space of a process. The memory space of a process is the portion of memory a process is allocated. Now that portion, as we will see later in the course, that memory space need not be contiguous in the physical memory. That means it doesn't have to be like these 10,000 bytes belong to this process. That's not the case. In reality, we can spread the process into different parts of the memory. But in the beginning, for the first few chapters, we will assume that the memory is allocated in a single chunk for a single process. It will be easier to explain and understand. Anyways, if you look at this memory chunk, this process memory space, it is composed of typically 4 sections or 4 segments. The first one is a text section. That's the section that contains the instructions. Now, where do these instructions come from? Well, they come from the program on the disk. Read the program, the executable file on the disk. You will see that it has instructions one after another. So you take those instructions and sometimes a little bit do transformation, but take those instructions and put them in the text segment. So the text segment, although the word text might sound you like a string, it's not a string. The text segment is the instructions of your program. Now, those instructions typically modify your variables. Now, you have local and global variables, as you know. The global variables are in the data segment or the data section. The local variables, remember, actually belong to the functions. So, where are the functions? Remember, a function typically is not alive when the program starts. It's only the main function that's alive. And the main function will call another function. So that function suddenly will start running, do what's expected of that function, and when it reaches the end, the function will terminate. It will exit and it will return probably some value to the caller function. And the caller function may later again call the same function or another function. All that caller function may also complete and return to its caller function. Finally, when the main function completes, the whole program ends. We know that. Now, as you can see, the functions that are currently executing change during the lifetime of the process. Functions start executing, then return, exit. Another function starts, that exits. One function starts, it calls another one, then they all go back. Now, all these are managed by the stack. We will be discussing the stack in more detail soon. So the stack contains all the information about all the functions that are currently in execution, and by that information, we mean actually the arguments of the function and also the local variables of the function. So again, pay attention. The local variables are in the stack. The global variables are in the data section. That's important. Now, while the program is running, you can, remember, do dynamic programming, which means you can, for example, allocate space for your pointers and later release them. So that kind of dynamic memory allocation is done through the heap. When you say new or malloc for a pointer, the memory is allocated from what we call the heap, and when you release it by saying free, then it will be returned back to the heap. Now, so once again, to repeat, in our process memory space, we have the text section, the data section for the globals, text section for the instructions, data section for the globals, the stack for the function calls, therefore also for the local variables, and the heap for dynamic memory allocation for your pointers. Now, all these four constitute the memory address space, but also actually, while the program is running, you also have some register values, which are also part of the process. Like you have AX, BX, whatever registers you have, or R1, R2, however you call them. For each CPU architecture, the name and the number and the format of those registers change, but the basic concepts are the same. All those general purpose registers, and also especially one special purpose register, which is the program counter. Remember, the program counter contains the address of the next instruction to be executed. So the program counter is also part of your process. So it is these four sections plus the register values. So according to our discussion, you should have realized that the program is actually a passive entity, a passive object on the disk. And when you run the program, actually it becomes active, and it's not the program that becomes active, but an active entity is created, which we call the process. So the process is created when it's created in the memory. The execution of the program, the running of the program, could be started either by double-clicking an icon on the in the graphical user interface, or you type the name of the program in the command line interface from the shell, or if you're talking about a touch screen, maybe you touch the icon with your finger. Doesn't matter. It's the same thing. In all cases, a process is created out of the program. And note that by repeating this, like clicking the icon again, you can create, for example, another instance of the program. For example, you start the calculator. So a process is created from the calculator program on the disk. And you click it once again. So a second copy is created. You click again, a third copy is created. Now you have three processes, all created from the same program, from the calculator executable program, but each one is a separate process. Each one actually has different values in their registers because you're calculating different mathematical expressions. Okay? For example, if one of them, for example, executes some illegal operation like division by zero, and assume that somehow the calculator program was written in a way that it could not handle division by zero, and if you do that, the program crashes. Okay? For example, if out of these three executions, out of these three processes, if the second process does division by zero, that will be terminated by the operating system because it executed an illegal operation. But the other two will remain. Nothing happens to them because these are separate entities. So that's something you should always keep in mind. So when a process is running, when you start a program from the disk, the instructions in the program, in the executable file, are placed in this text section. Now, by copying the instructions to the text section, the process is not completely created yet. Okay? You should also create the data section, and remember, the global variables are alive throughout the lifetime of the process. Therefore, the data section is also created, and global variables are also there. And don't forget, the data section, when the data section is created, first of all, the data section is cleared. It's all set to zeros. And then in that clean area, the global variables are created. That's actually why the global variables, even if they're not initialized, they're zero. Because the data section has been cleaned before the variable was created. So all bits there had been turned to zero. Pay attention, that's not the case for the stack and the heap. Therefore, the stack and the for the local variables, and also for malloc, calloc, or new, whatever, what you get need not necessarily be all zeros. Therefore, local variables are not initialized. Okay. Anyways, we've created the text segment. We have created the data segment. We create now for the other two, heap and stack. We don't have a single. We don't have two sections, but we have a single section. This is actually heap and stack together. Now, initially, when the program starts, the heap is completely empty. So it's not as much as you see in here. The heap is just this area. It's all zero. But the stack is actually not empty. It starts with, remember, the main function. Okay? Now, one thing to note is you have this whole section created for the heap and the stack, and the stack grows this way and the heap grows this way. So they grow towards each other. But remember that the process is an active object, so you're calling functions, so the stack grows. The functions end and they return values, and when you come to the end of a function, the entry for that function will be removed from the stack. Therefore, the stack will shrink. So the stack always grows and shrinks with the function calls and function returns. Similarly, the heap also grows and shrinks. When you allocate memory, you take space from the memory, from the heap. When you free a previously allocated memory block, then the heap shrinks this way. Okay, so throughout the lifetime of the process, the heap and the stack grow. Now, as long as this allocated space is greater than the size of the heap plus the size of the stack, then there's no problem. When the sizes of heap and stack added together reaches the size of this whole section reserved for heap and stack, then you have what we call a stack overflow or a heap overflow. One actually overflowing the other, one stepping on the other. And if that happens, now you have a problem. That means actually your memory model was not sufficient for this process and it failed. Okay, so you should be careful with how you use the heap and the stack. For example, when you try to use, for example, recursion, you should be very careful, because in an uncontrolled recursion, you call function f, which calls itself in a recursive manner. So another entry will be created. So an entry was created for f, which calls itself recursively. So another entry is created for f, and another is created for f. Now, if you continue this way, at some point, the stack will overflow the heap. Even if you don't do any memory allocation, finally, the stack will fill all of this reserved area for the reserved memory space for the heap and stack section, and you will have a stack overflow, and the program will crash. Okay, that's why actually when we use recursion, we should be very careful with the termination case. There should always be a termination case for that recursion, so that the recursion at some point ends and all these functions are then returned. And as these are being returned, the entries here will be deleted one by one. Finally, you will come to main. When main is also completed, the program ends. Similar is true for memory allocations. If you never return the memory you have allocated with malloc, calloc, neo, whatever you call that, you will finally run out of memory. Okay? That's actually why, for example, in C++, in the destructor, you should be careful to deallocate all the memory you have allocated for that object.